Good morning, everyone. My name is Jinxin Liu, a software engineer from ByteDance infra team. As we all know, applications on a append-only system must do garbage collection. Existing works mainly focus on the compaction, scheduling, or optimization. Today, I will propose a totally new garbage collection mechanism named DisCoGC, discard-based garbage collection, which achieves much lower write amplification without sacrificing performance. This work is co-worked by ByteDance and Tsinghua University. Here is the layered storage stack in ByteDance. The fundamental layer is a distributed file system called ByteStore. Many storage services are built on ByteStore, and finally, applications are built on those storage services. Let's focus on block device service named ByteDrive in ByteDance. ByteDrive exposes virtual block devices to users like a virtual machine, containers, etc. The virtual block device is also called volume in our system. The volume is divided into multiple segments for partition. In one segment, we convert the random write to sequential write by LSM tree-based index. ByteStore exposes the append-only log file to users. A log file is the basic unit of garbage collection in ByteDrive. And a log file is composed of multiple trunks. A trunk is the basic unit of fault tolerance. Each trunk's replica is stored in a special user file system named UFS on SSDs. We use append-only in ByteStore for the following reasons. First, it seamlessly supports EC for space efficiency fault tolerance. Second, it simplifies the data consistency. And lastly, its preserved history change feature makes it simple to do snapshot, version control, and crash recovery. Before DisCoGC, ByteDrive used a typical GC method, which we also call the compaction. The compaction procedure periodically executed to recycle stale data ranges. First, select target log files whose garbage ratio exceeds the threshold. Then copy the valid data in the selected log files to a new log file. Then do remap in metadata. And finally, delete compacted log files. The second step introduces the logical write amplification, and the stale data introduces the space amplification. This is the relationship of space amplification and write amplification in compaction. Lower space amplification results in higher logical write amplification because it needs more frequent compaction, lower garbage ratio threshold, and more reads and writes. And on the opposite, lower logical write amplification results in higher space amplification because it needs less frequent compaction, higher garbage ratio threshold, and more stale data remains in the log files. To find a better optimization, we do some trace analysis on ByteDrive. The workloads on ByteDrive are classified into three categories: online, SAR, and offline. We do trace at the volume layer. The basic information of the three traces is shown in the right diagram. First, let's look at the write workload dynamics. It shows SAR and offline workloads lack a predictable daily cycle, so do compaction during off-peak hours is unsuitable. And for write sequentiality, it shows SAR and offline workloads exhibit highly sequential writes. Finally, let's look at the fine-grained write analysis. It shows the SAR and offline workloads exhibit frequent overwrites, which causes large and continuous garbage in the log files. So we need a new GC strategy to leverage large continuous garbage. Our solution's inspiration point is to revisit discard as a GC mechanism. Discard is a mechanism to avoid reading valid data from all log files and rewriting it to the new ones. Here we showed a typical discard steps on log files. First, locate the stale range on log files. Then locate the data on SID and release the space occupied by the data. And then release the SID space. Then the released SID space can be reallocated to other files. It is simple to implement discard on a single file system. However, deploying discard on a multiple layers storage system requires special designs. In order to implement discard in our multi-layered storage system, we should first scan the metadata system to locate the to-be discarded ranges. Then issue discard requests on log file. At the file system level, we should locate ranges on trunk replicas and then locate clusters and modify metadata pages in UFS. And finally, record discarded ranges in metadata system. There are many challenges to implement discard in a multi-layered storage system. The first challenge is a boundary loss. In this example, block server uses a 2+1 EC to store data in log file. If it was to discard a 200 kilobytes range in a log file, the middle of the range is mapped to one entire EC stripe and issued to the trunk replicas. Two boundaries of the log file range can be reclaimed and become EC loss. And to the UFS layer, the middle of the range in each trunk replica maps to some whole clusters, we also call the allocation units, in the UFS and is reclaimed. But the boundaries can be mapped to any whole allocation units, so the boundaries become cluster loss. We observed that the discard operation is reentrant in the same discarded range. That means if a discard request issued to a discarded range, nothing happens. To solve the boundary loss problem, we use a mechanism called boundary extension. For example, range number 1 and range number 3 are discarded. They cause some boundary loss. If we discard range number 2 without optimization, the operation will cause new losses. But if we extend the discarded range to the adjacent discarded ranges, like this not only prevents new EC loss, but also eliminates previous EC loss. Another solution to boundary loss is configuring the strip unit size to the proper size to eliminate cluster loss. In the left side diagram, if 64 kilobytes unit size was used, only 3 clusters can be discarded per replica, which causes nearly 25% loss. So we adjust the unit size at the right side diagram, and the whole 4 clusters can be discarded per replica, which is 0 loss. The second challenge is frequent discard operations require many metadata updates in UFS layer, which causes contention for disk I/O and CPU. We use discard batching, which means the block server groups multiple discard ranges of the same log file into one discard request. This will reduce the metadata updates in UFS from multiple to just once. Block server also implements a parallelism-aware discard task scheduler to limit the number of concurrent discard requests. Despite the use of the batching and parallelism control, a large number of discardable ranges in segments will cause a burst of discarded ranges. We employ a discard flow control mechanism in block server. It limits the maximum discard IOPS to mitigate performance impact. The third challenge is discard increases the metadata management overhead in block server. Because discard causes fragmentation in log files, block server needs more memories to store the sparse data ranges. Compaction can gather fragmented valid data, lower metadata overhead. We found that compaction and discard have complementary effects. Compaction can prevent fragmented log files and chunks by moving data, but incurs write amplification. Discard is the inverse. Our solution is to use a lightweight, high-frequent discard as a primary mechanism and use relatively low-frequent compaction to mitigate fragmentation. The fourth challenge is insufficient trim LPS of some SID. We found some SID models' trim LPS is so low. Just like model B in this diagram, it only supplies 6,000 trim LPS. This may delay space reclamation, potentially exhausting UFS capacity, and cause system failure. And it also results in a higher SID space usage, leading to aggressive SSGC. Aggressive SSGC may cause a large physical write amplification. We observed consistent latency for subsize threshold trims, which means trim latency remains lower and consistent when the trim size is below a certain threshold. So in order to optimize trim efficiency, we adjust the trim size to approach the threshold. Based on the observations above, we implement trim filter and merger in the UFS. The filter issues trim only for larger ranges. This reduces the number of trims without increasing trim latency. Trim merger merges small ranges adjacent in LBA into a large range, which can be trimmed by one command. For evaluation, server config is listed on the left side. This config is widely used in our online system. Online cluster is a large-scale production cluster with production mixed workload, while offline cluster is a ByteDrive plus ByteStore cluster with 10 servers. Its workload is replaying 3 traces and using FIO benchmark. We counted the invalid range size in the production cluster and found that ranges larger than 128 kilobytes account for more than 19%, while ranges larger than 1 megabyte account for more than 17%. So the mixed workload in the production cluster is well suited for DiscoGC. From the performance perspective, DiscoGC's LWE, which means logical write amplification, is 32% lower than that of the compaction-only GC. The space amplification is 10% lower, and the physical write amplification is 10% higher. The total TCO is 20% lower. Meanwhile, the average latency nearly does not change, and the 99% latency is much slower. DiscoGC significantly reduces TCO in production clusters. In the offline clusters, for SAR and offline workloads, DiscoGC's TCO is much lower, which means DiscoGC saves TCO greatly in suitable workloads. For online workloads, DiscoGC's TCO is a little lower, which means DiscoGC is robust and can still save a little TCO in unsuitable workloads. These diagrams show that adopting DiscoGC has nearly no impact on front-end latency for each workload, some even lower than that of the compression only. Some lessons learned from DiscoGC. The first one is, should we adopt DiscoGC? Sequential workload with frequent overwrites is good for DiscoGC. If you are not sure of that, please do trace analysis first. The second one is how to deploy DiscoGC safely. Our advice is to deploy in stage. Use mock discard during the canary deployment phase. The third one is how to monitor DiscoGC. You should alert when the discard ratio is smaller than 18% with a higher SID space usage. If the CPU and IO are not high, use aggressive discard scheduling. If the CPU and IO are busy, throttle offline IOs. If there is no offline IOs, do data migration. The fourth one is, do we need trim optimization? For SIDs with high trim LPS, like Model A, enable trim only, disable any optimization. For SID with low trim LPS, like Model B, enable trim filter at merger, and tune the filter size to constrain the trim LPS to below 85% of the SID's maximum trim LPS. In conclusion, compaction faces a space amplification and rate amplification trade-off. Our trace analysis shows SAR and offline workloads is suitable for discarding. Our solution is to use discard to leverage large continuous garbage. We do boundary loss emulation. We did discard batching and scheduling. We did a coordination of compaction and discard, and also trim filter and merger. Finally, DisCoGC optimizes space amplification, rate amplification trade-off to lower TCO with nearly no impact on latency. Thanks for your attention. Questions are welcome.